Welcome back. This is Mr. Hassan's Maths channel. I'm now going to be answering question number 5 from the October 2023 International A-Level Mechanics paper from Edexcel. It's an M1 paper, and we're here told about a small ring of mass 0.2 kilograms is attached to one end of a light and extensible string. The ring is threaded through this fixed rough vertical rod. The string is taut and makes an angle of theta with the rod, as shown in the diagram, where tan of theta is 12/5. Given that the ring is in equilibrium and the tension in the string is 10 newtons, find the magnitude of the frictional force acting on the ring. So there's a few important points here. One of them is that we have a ring. Okay, it's not just a particle, it's a ring. Okay, and we have a light inextensible string, which is attached to it. And the ring is threaded onto a fixed rough vertical rod. The string is taut, okay, and the ring is in equilibrium. Okay, so those are all very important points that we're going to discuss here. So let's first of all, let's look at some of the forces acting on the ring. Okay, so you have its own weight which acts vertically downwards. Okay, its own weight which acts vertically downwards. So the weight of the ring is going to be acting down. So that's the weight, which is 0.2 g newtons. My highlights are on there. Okay, so 0.2 g newtons. That's the weight of the ring. We also have the tension acting in the string, which is 10 newtons. Which they told us is 10 newtons. Okay. Other forces that would be acting here, very important one, which for the first part of the question doesn't really affect much, but you're going to have a reaction force which must act in this direction. Okay, this is the tension in the string. There's a reaction force that must act in this direction in this case. Now, whenever you have a ring threaded through like a solid object, like a rod, there's going to be a reaction force, and it's going to always act in a direction perpendicular to the surface of the rod, the surface that's threaded through. Okay, if it's threaded through a string, then that string is not a solid surface, so there won't be a reaction force between the ring and the string. Okay, so if it's some questions, there's a string threaded through a ring, and it's a string. It's not a rod. It's not like a solid object like a rod. Okay, a rigid surface. It's not a rigid solid surface. That's a string, which is, it bends and buckles. So there's not going to be a reaction force. But if it's a rod, there will be a reaction force, and it will always be perpendicular to the surface of the rod, and it always acts in a direction that, if it's in equilibrium, will keep it in equilibrium. So if there's a tension acting in this direction, and the only other forces going to be acting are going to be the weight, which will be acting down, and the friction, which will be acting parallel to the surface, because the friction acts in the direction of movement. It'll either move up or down, for example. Then the only other force, if there's only one force going to have a horizontal component in this direction, the reaction must be there in this direction to balance it out. Okay, if there were other forces acting, like if there was another tension this way, then we'd have to try to figure out the reaction could be in either side, depending on what it needs to be to keep this thing in equilibrium. Okay, in this case, there's only one force going to be to the right, have any component, therefore the reaction must be to the left for it to be in equilibrium. Okay, so that's a few little points there that were important. Okay, so we've talked about ring, threaded, rough vertical rod means there's friction, light inextensible string means that the tension is the same all the way through the string. Okay, and we don't consider the weight of the string. So now we got to decide to find, we know that there's frictional force acting. Now we don't know in which direction it's acting. Okay, we're going to work out what the frictional force is, and part B says the direction in which it acts. Okay, so first of all, let's resolve this 10 Newton force in the vertical direction, because that's what we're concerned with here. So I'll just change the color. So this is the 10 Newton force. I want to resolve it vertically, so I have to go into the angle theta given. So I'm going to resolve it vertically, going into the angle, so we use cosine. It's like we're looking for the adjacent side. So this is the cosine. This is going to be 10 times going into the angle, cosine theta. 10 cosine theta. What happened there? 1 second. So that is the resolving of this force vertically. Okay. Now these two forces together, okay, they have to balance out. Okay. The difference between them, okay, will be the frictional force. Okay. The difference between them will be the frictional force. So the magnitude of the frictional force is going to be the magnitude of the difference between these two. Okay, so it's going to be the magnitude of the difference between 10 cosine theta and 0.2 times g. The difference between those two will be the frictional force, the magnitude of the frictional force. For us to know the direction of it, we'll have to see which of these is bigger, and then the frictional force has to basically be on the side which is smaller, so that it balances out the other force. Okay, because it has to be in equilibrium. So the magnitude of the frictional force is going to be equal to the difference between these two forces, and so we can work that out. So now we know that tan of theta is equal to, as they told us, 12 over 5. 12 over 5, the tan of theta. So if we were to draw a small little right angle triangle just to picture what's happening here, we're going to have a right angle triangle. Okay, and we'll say that this is a right angle over here. Let's say that this is theta, and opposite it would be 12, the adjacent would be 5. The hypotenuse is going to be 13. 5, 12, 13 triangle. If you're not sure, 5 squared is 25, 12 squared is 144, 144 plus 25 is 169, the square root of 169 is 13. So we can see here from this that the sine of theta will be opposite over hypotenuse, 12 over 13, and the cosine of theta is going to be adjacent over hypotenuse, which is 5 over 13. All right, so we got here the magnitude of the frictional force is going to be the magnitude of 10 times 5 over 13 minus 0.2 times 9.8. So that's going to give us what? Let's work that out. We're going to have 10 times 5 over 13, which is 50 over 13, minus 0.2 times 9.8, which gives us 1.886. So that's going to give us the magnitude of 1.886, which is basically 1.89 newtons. Now we can see that because this is bigger than that, the friction must act upwards. Okay, act downwards. Why? Because 10 cosine theta minus 0.2 times 9.8 gave us a positive value. Okay, so it says state the direction of the frictional force acting on the string. Now we can see that the upward force 10 cosine theta. Okay, so we can see that 10 cosine theta is greater than, okay, 0.2 g. Okay, we worked that out because we subtracted, that was 10 cosine theta. Okay, 10 times 5 over 13 minus 0.2 times 9.8. It gave us a positive value, which is going to be the value of the friction, but that's going to act in a direction to keep this in balance. So if this is greater than that, the friction is going to act down. Friction force is going to act downwards, therefore, because the frictional force will act down here, okay, and it will be enough to keep it in equilibrium. So we can say that the friction, okay, must be downwards, okay, acts downwards so that the forces balance out. So this will be the same as that. Upward force and downward force has to match. Okay, so there's the answer to part A. And now we're going to do part B. Now, if we had done this the other way around, if I had done 0.2 g minus 10 cosine theta, only thing would happen, this would be a negative. And we would have said the answer is still going to be the friction force still going to have this magnitude. Okay, because the magnitude, we just care about the size and not the direction. But also then we'll realize that, you know, if we subtracted it the other way around, we would realize that, you know, the friction has to act down still, all right, because we saw that this is bigger than that. Because if we subtracted the other way around, we would have got a negative answer. So same thing would apply. It doesn't matter which way you subtracted, you would still, in the end, have the same answers here. Okay, now for part C, it says the coefficient of friction between the ring and the rod is a quarter. We also know already that the sine of theta was 5/13. No, 10, that was 12/13, sorry. And the cosine of theta was 5/13. We know that from before. Okay, so it says, given that the ring is in equilibrium and that the tension in the string T newtons can now vary. So now we have a tension in the string which is not 10. It can change. Okay, so we have a tension in the string which can vary. It's a bit big, but no problem. We have the weight of the ring, which is still the same. Okay, 0.2 G newtons. You have the reaction force. Okay, those are the forces acting. But now it says, given that the ring is in equilibrium, so it's in equilibrium still. It's not moving. And the tension can vary in the string. Find the minimum value of T. Now, what does that mean? Minimum value of T. Okay, so what it means is, this is a very common type of question in statics. So the minimum value of T means the smallest value that T can be such that this thing remains in equilibrium. Now, how do we think about a question like this? Imagine the tension wasn't there. Supposing there's no tension. What would happen to the ring? Okay, you'd have friction acting upwards in this case because it will want to go down. Okay, so the friction would be acting upwards. Okay, and if the friction was not enough, okay, if to keep it staying where it was, it would move down. So the minimum value of the tension is the amount that's needed to just prevent the ring from sliding down. Okay, so you can say T minimum, the minimum value of T min, I'll call it T minimum, okay, is just enough to prevent the ring from sliding down, the rod. Okay, so therefore, okay, if it's just about to slide, it's in limiting equilibrium. Okay, it's in limiting equilibrium. It's in the limit of its equilibrium. Okay, which means that the frictional force that's generated is the maximum value of friction that can possibly be. It's called F max, because we know that the frictional force can vary between 0 and its maximum possible value in that situation. Like, for example, you have something on the ground, you pull it this way, it's a rough ground. If you don't pull it, there'll be no friction. Friction will be 0. But if you pull it, then the frictional force will match whatever that pulling force is. It will be the same. If that's 1 Newton, that will be 1 Newton. If that's 2 Newtons, that will be 2 Newtons. If that's 10 Newtons, that will be 10 Newtons. It will just match it. It will stop the thing from moving. It will never be more than it. It will always just be enough to match it. But friction has a maximum possible value that it can reach, F max. And that's given by what's called mu, which is the coefficient of friction, times R, which is the reaction force of the surfaces that are in contact. So depending on the value of these two, the frictional force has a maximum value in any given situation, all right, which it cannot exceed. So in this case, we're thinking about the minimum value of T is going to be the value of T such that this thing is about to slide down and, you know, the frictional force has reached its maximum possible value, because together the component of T in this direction and the friction is going to stop this thing from sliding down. That's what they're going to be doing together. So the component of the tension in this direction, let me just move this F max on this side so it's clearer. So the component of the tension in this direction plus the friction, and this is going to be T times going into the angle cosine theta. T times cosine theta plus the friction has to match this. Now, if the frictional force, if for example, if the value of this gets less, the value of this is going to get more. They have to match that. So if the tension, okay, is going to be less, if this T cosine theta gets less, cosine theta gets less, this has to become more. If this gets even less, it has to become more. Why? Because it has to be in equilibrium. So these have to be, it has to match the 0.2 G newtons. So we're going to find the situation where the T cosine theta has reached a value, okay, such that F max cannot be any more bigger than that. It's reached its maximum value of the friction. And then therefore, if you make T cosine theta any less, this can't get any higher. So if you make T cosine theta any less, it won't be in equilibrium because this will get less and this can't get more anymore, right? As this gets less, this increases. As this gets less, this increases. We're trying to find the point where this has reached the value such that this cannot increase anymore. It's reached its maximum possible value, and that's the value of T that we're looking for. Okay, so we need to find what F max is. That's one of the keys to this. F max is equal to mu times R. Now mu is equal to a quarter, and R is equal to, we have to resolve this force now in the other direction. So we have to resolve this in this direction over here. So we're going to take the T, and it's going to be in this direction. It's going to be going away from the angle. So this is going to end up being T times sine alpha. T times sine alpha. So we know that R is equal to, if we resolve this way, R is equal to T sine alpha. So we got mu R is equal to a quarter times T times sine alpha, which is going to be, we know sine alpha is 12 over 13. So it's a quarter times T times 12 over 13. So you got 3T over 13. So I'll leave it as 3T over 13. So F max is equal to 3T over 13. Okay, that's F max. Okay, so we know if we resolve vertically, we've got T cosine theta plus F max must equal 0.2 G. Okay, they must be balanced out. So T cosine alpha is going to be T times, now the cosine of alpha, as we deduced before, was 5 over 13. So you have 5 over 13T plus F max, which is 3 over 13T, is equal to 0.2 times 9.8, okay, which is going to be 0.2 times 9.8, which gives us 49 over 25, which is 1.96. So therefore, we can see here we're going to end up getting 8T, okay, is equal to 13 times 1.96. So T is going to be 13 times 1.96 over 8. Okay, just have a common denominator there. So you end up with 13 times 1.96 divided by 8. So I have 1.96 times 13 and divided by 8, which gives us 3.185. That's 3.185. To 3SF, we can say 3.19 newtons. So that's the tension. Okay, the minimum value of the tension in the string such that this thing is in equilibrium. Okay, now for part 2, it says find the maximum value of T. So the maximum value of T would be such that it's in equilibrium. All right, so basically now the minimum value is a T that's just enough to stop it from sliding down. Now, if you increase the value of T, then this component will increase more and more and more and more, okay? And it will reach a level where, it will eventually balance out the weight, and it's going to be, the ring will be wanting to slide up the plane, okay? But it's a rough plane. So the friction now will start acting in the opposite direction because the friction always acts in a way to prevent the motion. So as you increase T, it gets bigger and bigger and bigger, it's going to be trying to pull the ring up the slide eventually. The higher it gets, okay, the force up is going to get more until eventually it's going to start sliding up the plane, okay? But the frictional force will prevent it. So we want to find the value of T such that it's just about to slide up the plane. So the frictional force, okay, is going to reach its maximum possible value, okay, so that its force plus the weight will balance out that T, that's component of T that's trying to pull it up. So when it's just, if we want to find the maximum value of T, we're trying to find the value of T such that the ring is just about to slide up. Okay, so the value of T maximum is going to be, okay, it's going to be the value of T such that, sorry about my bad writing, the ring is on the point, you can say, on the point of sliding, this time up the rod. Okay, so I hope that was clear. So now basically it's going to be the same equation as we had here, except this time acting up is T cosine theta, but acting down is the weight and the friction. They're both acting down to prevent it from going up. So we have the same kind of situation. T cosine theta is 5T over 13. We have 0.2 times 9.8, which is 9.6. But this time we're adding the 3T over 13 on this side instead of that side. Okay, so now when we rearrange this, you're going to have 5T over 13 minus 3T over 13, which is 2T over 13, equals 1.96. So T, therefore, is going to be 1.96 times 13 divided by 2. Instead of over there, it was divided by 8. Now it's going to be the same thing, but divided by 2. So that's going to, of course, give you a bigger value when you're dividing by a smaller number, which is going to be the maximum value of T. So I can even go back to the calculation that I have here. Okay, can I? Okay, no, forget it. Let's do it again. So we're going to have 1.96 times 13. Now, this time it's going to be divided by 2, which gives us 12.74 newtons. We should really write it to 3SF, so 12.7 newtons. That's the maximum value of T, and here we have the minimum value of T. Okay, so that's a very important question here for us to understand. A lot of students were confused about this question. I hope this makes it clear. Okay, so I hope this makes it clear, this question. So we've completed question number 5. Other questions from this paper will be found in the playlist, which will appear in this section at the end of the video. Other questions from the topic of statics, which is all about, will appear in this playlist over here. I will make a special playlist for just dealing with these questions about rings in statics in this area over here. You can subscribe to my channel by clicking on this link. Thank you for watching and see you soon.